Thanks. So the next speaker is indeed Joseph Razavi from the University of Manchester. Please go ahead.
Thank you, and thank you to the organisers for the wonderful conference. This is joint work with Andrea Schalk, and we're going to tell you how to make Gandy machines easy using category theory. So first, I'll tell you what Gandy machines are. So Robin Gandy proposed a model of computation based on two principles, and the idea was to take the conceptual insights that Turing used to define Turing machines and try to generalize them a little bit to match physical machines that can do many things at once. And the two principles are that states are finite objects with a bounded amount of local detail, and changes of state propagate through these states at a bounded speed. And even though this is defined as a model of computation, and that's where my interest is, you can think of these as causal systems which have a particularly nice, simple causal structure. So what kind of systems do we have in mind? Well, one example, this is what we'll use as a running example, would be cellular automata. And our states have to be finite. So here you see that when we update this state, the boundary gets removed because this is a finite object and we don't know what to do with those boundary cells. This is probably the simplest example. That's why we'll use it as the running example. But we could do more complicated things. For example, if you took something like interaction nets, and if you do every possible rewrite all at once so that you get a synchronous system, then this will also be an example. So this shows that you can have complicated changes of shape and things can grow in size and not just shrink, as in the simple example. So how did Gandy actually axiomatize this mathematically? Well, his idea was to use hereditarily finite sets. So it's as if he was thinking that if you were to write down your own model of computation which satisfied these principles, you might do it in set theory, and then he wrote down some very general constraints which it's very likely your model would satisfy if you wrote down a set theoretic version of it, which satisfied his principles. So this is very general, but these constraints are quite difficult to work with. And an important feature is that he has a countable number of atoms in his set theory, which kind of act like coordinates. And there's a very delicate and sophisticated treatment of coordinate invariance, because of course your coordinates can't be part of your bounded local detail, so the dynamics has to be invariant. But people who have worked on these ideas subsequently have tended to pick particular structures. So one nice example of this is Arrighi and Dweck, who use a certain kind of labeled graphs. And these are easier to work with, which means that they can conduct more detailed studies of the behavior of these kinds of systems. Now, in this talk, we're going to use categories as the basis of our axioms. And you might think that's just because we like categories, but in fact, in all of these models, you have to talk about partial states, and you have to talk about the ways in which these partial states fit together to build up bigger partial states. And so there's always a category lurking in the background. And the idea is, what would happen if we just work with this category directly rather than a particular model of this idea? So in our running example, the parts of states are these little colored grids with black and white squares. And the morphisms are ways in which one of these grids can fit into another. And I'll sometimes highlight in a different color the image of a morphism so that you can tell where this morphism lands. But that's not part of the object. The object is just black and white. That's just me highlighting what the morphism does. And then our one step of computation will correspond to an endofunctor on this category of states and parts of states. And here's what it would do to this piece here. And you might notice if these are Conway's game of life rules that we're using, we do actually know the fate of some of these cells on the bottom, but we still remove them because the functor also has to encode somehow how the space is patched together out of its parts. So you always want to remove the boundary. Now we'll write down the first of Gandy's constraints in terms of categories. So that's going to be that these objects are finite and have a finite amount, they have a bounded amount of local detail. And so we'll start our definition and we'll leave a space to continue it later. So a categorical Gandy machine is a category C and an endofunctor U on C. And our first constraint is just on the category C. We demand that it's locally finite in the sense that all of its Hom sets are finite sets, and it has a finite dense subcategory. So in our category of black and white grids, if we look at this 2x2 grid in the middle of this diagram here, well, we can consider all of the morphisms from single cells and little strips of 2 cells into this 2x2 grid. Those constitute a finite subcategory, and this grid is the co-limit in this category of all of the morphisms into it. So the subcategory is dense. I should say that for most of this talk, I'll treat these objects and morphisms at an intuitive level, but at the end we'll come back and give a little bit of a more detailed definition of them. So what about the next constraint, which is the bounded speed of propagation? Well, to do that, we'll think about this in terms of kind of causal neighborhoods. So if we take a state that we want to update and update it, then we might pick out a small part of this updated state and ask for a kind of causal explanation. Why is it that there was a black cell located here in the update of this state? Now, here's, and it's worth thinking about what this is a picture of. So here I have a morphism, I have an object of C and a morphism into U of something, and I remember the thing which I am updating. And that's exactly what a morphism in the comma category of C over U is like. So this part of the picture is kind of a way of drawing a morphism in that comma category. And the fact that we remember the input is important. So what kinds of things could explain why we ended up with a little black cell here? Here's one possibility. So I could say, well, I had this smaller part of this state, and if I updated that smaller part, I would have got this thing, which would fit into the top corner here. And crucially, the thing I wanted to explain would factor through this. And so it's a kind of causal neighborhood of this phenomenon that happened in the output. But I think you can see that this isn't the most efficient explanation I could have chosen. And in fact, we know that in a system which conforms to Gandy's principles, because changes propagate with a bounded speed, we expect to find a kind of region whose radius, in some sense, is related to the speed of propagation. And in this cellular automata, changes or causal signals propagate one cell at a time. So we're kind of expecting a region of radius 1 to explain this single cell. Indeed, there is such a thing. In this case, it happens to update to exactly the thing we wanted to explain. No, that won't happen in every Gandy machine. But what we will have in every Gandy machine is this smallest causal neighborhood. And it's special because given any other causal neighborhood, there's a unique morphism from the smallest one into the arbitrary one. So yeah, the constraint on the speed of propagation then gives us a universal property And so we can ask what's actually going on here, category theoretically. So let's go back to our unfinished definition. That was the part we had before. And we can now fill this in. So we asked that this functor, which I call U triangle, I'm not sure if it has a standard name, maybe somebody can tell me. So what this functor does is it goes from the comma category C over C, so just the objects are just morphisms in C, to C over U, and it just evaluates U. So given f from x to y, it evaluates U on f, it evaluates U on x, but it remembers y. It doesn't actually evaluate U on y, and the comma category is defined so that this makes sense. So we're asking that this functor U triangle have a left adjoint, which I'll call f. Now, this condition, I think, is saying that U, our original functor, is a parametric right adjoint. And I hesitate a little bit there because when we first started looking into this, people who defined parametric right adjoints in the literature that we found then always defined them in the case where C has a terminal object. And in our examples, it's very, very rare that the category will have a terminal object. But happily, one of the reviewers actually told us that this condition is being a parametric right adjoint and pointed us at some more literature. So if anyone has a favorite characterization of parametric right adjoints, I'm very interested to hear it. Now, in some sense, this condition says that changes propagate. We have to add a finiteness constraint on this, which I'm pretty much going to sweep under the rug. So there it is. It's about preserving having a finite image on the domain for certain subcategories. Now, this is a little bit unpleasant compared to the first two, but because of the way this is structured, it's just saying that something is preserved by f. For lots of proofs that you want to do, this property just gets kind of carried around. So that's our complete definition of a categorical Gandy machine. Now, at this point, you might say, well, this is supposed to be a model of computation. So if you give me such a thing, is there a way of computing what U does? Can I at least compute one step of computation? And the answer is yes. And again, I'm going to sweep the details of this proof under the rug, but there's one point that I want to make about it. And that is that the proof goes just by constructing this pasting and then showing that it has nice properties. And most of these properties you can prove just using the universal property of the comma category. And then only right at the end do you actually look at the finiteness conditions you've got and do a little bit of concrete work to convince yourself that you really can compute. But you convince yourself that this is a pointwise can extension and that it's very nicely behaved. And then the finiteness condition means that you can actually compute this. B here in this diagram is any finite dense subcategory of C. And that gives you kind of a notation for your objects. And then this can extension, because of the finiteness condition, gives you a way of computing what U does for that representation of objects. So now let's think about this example and let's try and move a little bit towards an actual definition. So we can think about the blank grids as being categories enriched in the group Z squared, where we think of that as a discrete monoidal category. And there's a nice NCAT Cafe post by Simon Willerton where he talks about torsors as enriched categories. And if your group is abelian, then you get a symmetric monoidal closed category of enriched categories. And so these are a bit like torsors, because given any two of these cells, there's a kind of z² value distance, or there's a z² value displacement that's unique that gets us from one to the other. But they're kind of like partial torsors, because there are some elements where not every, in fact, for all of these cells, not every displacement in z² is defined. And we have to put some conditions so that we get nice objects. In particular, we have to put some kind of connectedness condition on these objects so that we make sure we have a finite dense subcategory. And depending on what connectedness conditions you get, proving that your monoidal structure still works for that subcategory can be made slightly nicer or slightly worse, depending on whether, for example, you only want rectangles or if you want kind of L-shaped regions as well, which can be nice for giving some kinds of examples. And in this case, the monoidal structure, the monoidal product behaves like Minkowski sum or like dilation in image processing, and the internal Hom behaves like erosion in image processing. And it's quite nice and pictorial, because your internal Hom is really somehow like the set of places where the thing that you're eroding by fits inside this one. But this actually emphasizes how coordinate free this version of doing things is, because, for example, we kind of intuitively think that this cell here is the middle of this little neighborhood, and therefore that this 2x4 block fits in the middle of this one here. But actually, the formalism doesn't say anything about that. This could be the neighborhood of the top cell. It might be that information moves at twice the speed, but it only moves up and to the left. And we could define a kind of version of the game of life where, after you update your state based on the rules of the game of life, you move the whole universe up to the, or down to the right, I guess you would move it. And if you're working in a coordinate-based model, you can detect that the whole universe has moved down to the right. But in this version, you can't, because there's no canonical. There are many maps from the eroded version into the big one, but there's no canonical one unless we pick a point in here. So that emphasizes the way the kind of invariance properties that we want can be very smoothly treated in using tools from category theory. So, okay.
You have 1 minute left, just to remind you.
Thank you. So these blank grids are all very well, but I promised you the game of life, and clearly this isn't it. But if I think about the category of colored grids, you can see this as having a projection down to the uncolored grids, and this projection is a discrete vibration. And we have this proposition, which is extremely easy to prove, that if I have a Gandy machine U, which might be my game of life here, and I have W, which might just be eroding the blank grids, and I have a discrete vibration going from one to the other, making this diagram commute, then U is a Gandy machine. And now future work I won't go into in too much detail, but if anyone knows any nice category theory that they think might help build examples, let me know. There's a very nice topological characterization of Gandy machines, which I think might interact with this very well. And if you want to know about my original motivation, which was somehow about how information flows during the computation, so properties which are initially global properties get shrunk down to local ones, I think this should be a nice setting to study that question, and you can ask me afterwards, I guess, if you're interested in that. Thanks. Oh, there are some references.
All right. Thanks for this talk. Very nice talk. Let's thank Joseph first. Okay, there were several questions in the chat, but I have the impression that most of them have been answered. If someone would still like to, maybe Phil, is it correct that your question is perhaps still.
I'd like to ask a question. Is there a converse to the first proposition? That is, can you simulate every Turing machine?
Yes, every Turing machine, yeah, you can. And I've almost proved this in some sense because you can simulate a Turing machine with a cellular automaton.
Yes.
The difficult part is that this simple model of cellular automata always shrinks the states, which means you have to provide enough kind of buffer that you know that your state won't shrink to nothing before the answer comes out. But you could devise a more complicated version where you have boundaries where the states are allowed to grow, and that would be a more satisfying way of demonstrating that you have a Turing complete system. Or if I'd spelled out the interaction nets version properly, then that would have also been a proof of that.
Yeah, thank you. Let me add a comment that I think that Robin would be very happy with this.
Oh, thank you very much.
Nice. There's a question from Juan Malero. Please go ahead.
Hi. So I have two observations / questions. The first one is regarding behavioral meteorology, which we'll have a talk later this week about. If I recall correctly, in the original paper, they mentioned a duality between space and behavior. And in this formalism of Gandy machines, we have morphisms representing like embedding of subsystems into other subsystems. What do you think about that duality? I mean, you could invert it and talk about the space of behaviors in a subsystem being projected onto the subpart.
Yeah, so I would very much like to understand how those types of things are related to this. I don't think I have a good answer for that. But I definitely think that at a deeper level, hopefully this axiomatization will give me a good way to study these systems. And I hope that at a deeper level, that kind of structure appears. So thanks. If you have any tips, let me know after.
Yeah, I have a second observation too.
Okay.
In the functional programming community, I think that there's a well-known example of cellular automata being implemented like comonads. And in that sense, you have a way of giving local update rules, and that kind of scales to the whole system. And I don't know, maybe I don't have any specific observation, but maybe there's a relation, a way to formalize in this framework the cellular automata, which takes into account the idea of taking local rules and expanding them to the whole system.
Yeah, I think if I understand the remark correctly, that's to some extent what this pointwise CAN extension will do, because the local rules will be related to things happening on the finite dense subcategory, and the CAN extension will extend them to the whole space. Thanks.
Okay,
so
that must be.
Okay, there's one more question. If it can be stated and answered quickly, we can take it. Philip Buric, please go ahead.
Hopefully, yes. Thank you. Very interesting presentation. I have only a tangential question, so just out of curiosity, have you considered categorical Gandy machines in the context of Kolmogorov complexity? Maybe it actually touches upon your initial interest with information flow. Do you think it would help, or how would that look? Because as far as I know, it's universal Turing. It's like Turing machines, mostly.
Yeah, I'm not really an expert on Kolmogorov complexity, but I hope that because you have access to the kind of causal structure of this system in a very nice way, and the causal structure has been designed to be very simple, I hope that you will be able to get at some kinds of questions of complexity, or the difficulty, for example, of shrinking a global property down. But it's very early days for that kind of question. But thanks.
Sure. Thank you.
All right. then I would like to end the session, and of course thank Joseph one more time for his nice talk.